Our project is Clear, sponsored by VoltServer, which stands for Colored LED Event Automated Reader. Our technical directors are Camille Gerardo and Stanley Mylinick. Our team is composed of 3 designers, 2 being electrical engineers, myself and James Kai, along with 1 computer engineer, Aramo Mayan. VoltServer is a company based in East Greenwich, Rhode Island, most known for developing and distributing a platform called Digital Electricity, which is a safe and innovative power distribution platform. The goal of this project is to develop a mountable LED sensor system to visually analyze RGB status LEDs and blink sequences incorporating VoltServer products. This will eliminate the need for VoltServer technicians to verify and decipher them manually. In order to meet our ABO, it would mean we would have to develop a 1.5-inch by 1.5-inch mountable PCB that would be able to be used on any VoltServer device. Along with this, the development of a sensor system that would be able to read status LEDs and blinking sequences and decipher them to the user is necessary as well. To achieve our ABO, we would also need to provide all schematics, layouts, fabrication, and assembly files related to the PCB, along with all firmware and software source code. We would also need to provide a complete bill of material along with a detailed system user manual. We were able to achieve our ABO. This is a list of all the technical team accomplishments we were able to make towards our ABO this year. This product, as for an economic impact, this product would allow VoltServer technicians to save time and therefore be more productive, saving the company time and money by automating this process. Given how standard LEDs are used to show diagnostic information, automating this process for quality assurance would result in a possible improvement in end-of-line testing. Below is a block diagram of how the overall project will function. I will mainly be discussing the LED sensor algorithm along with component research and the PCB mounting solution. This is a list of my key technical contributions this year, where I was able to create an LED sensor algorithm flowchart along with conducting component research and selection, redesigning the LED sensor and multiplexer schematics, along with developing a PCB mounting solution, along with a user manual and bill of materials. The flowchart was made to aid in understanding the preliminary design of the sensor algorithm, where after turning on the device, it would have to verify ambient light, then subsequently attempt to calculate what RGB colors would be present, and afterwards calculate the length of the signal, then relay the status LED code to the user. The part we selected was utilized in last year's team, the APS 5130 PD73P22 RGB color sensor. It's a 4-pin component that has 3 different photodiodes within it, so it's able to detect red, green, and blue signals. Due to the fact that we had a 3x4 array that we decided to make, it would mean that we need 36 output RGB signals to calculate. To account for this, we decided to use the CD74HC4067 multiplexer. It's a 24-pin component that has 16 present input signals, where we only need to utilize 12 of these for our design. As for the PCB mounting solution, our team was able to develop a PCB housing and mounting solution. The mounting solution is composed of several different parts, being the PCB housing itself, shown on the bottom left of the bottom image, the PCB cover, the TX550 mounting bracket, along with the TX550 cover, which fastens the card to the enclosure. Along with this, to reduce any possible light, we also designed some plugs for the 9-volt and DC jack. The next designer is computer engineer Aramo Mayan, who will be sharing his technical contributions over this year.
My technical accomplishments include researching parts, aiding in the collection of sensor data, researching the PIC microcontroller, designing the PCB layout, interfacing the PCB with the firmware, and developing a graphical user interface for relaying the blink sequence patterns to the user. The microcontroller that we decided to use for the operation of our software is the DSPIC33 16-bit microcontroller by Microchip. It features 80 pins, 69 of which are I/O pins, and 24 of those are able to be analog to digital inputs. It has the ability to have a clock frequency of up to 100 MHz through a software PLL, which stands for phase locked loop. Originally, we had planned to use a 36 MHz external oscillator as a clock input, but decided it would be more efficient to use the PLL. This increased clock frequency allowed us to be able to easily measure LED blinks within 1 millisecond, which was part of the anticipated best outcome. I also completed the design of the PCB. It is an 8-layer board with the top and bottom layer, 3 layers dedicated for routing traces, and 3 layers for the 5 volt, 3.3 volt, and ground planes. I was able to meet the required size of 1.5 inches by 1.5 inches. It features a DC jack and 9-volt battery connector paired with 3.3 volt and 5 volt voltage regulators to supply stable voltage to the components. It also contains the 12 3-in-1 RGB sensors, which are selected through the multiplexer to be read by the microcontroller. Lastly, it features a UART to USB converter to communicate between the microcontroller and computer. I also designed a graphical user interface using Java in order to visually display the status of the VoltServer device. You're able to specify the COM port and baud rate of the UART signal. It also displays the live LED feed read by the sensors on screen. There is also a button to get voltage readings from the microcontroller. I will now let my teammate James speak.
Thank you, Aram, for the introduction. My technical accomplishments over the past year include redesigning the power supply system for our PCB, conducting multiple tests on the photodiode sensors and collecting that data for later use, developing the firmware for the PCB in embedded C, creating the algorithm to process light from the LED using the test data, and continually testing the firmware to improve the accuracy of our algorithm. In the beginning of the project, we developed the testing apparatus being shown on the top left of the screen. It was designed to be very inexpensive and easy to manipulate. The LED is held over our PCB of sensors using only wooden dowels that support a sheet of cardboard cut with a circular hole for the LED to slide through. The LED is then connected to a breadboard along with the resistors for our sensor. The example circuit in the middle shows our test setup for the sensor circuit, including the 3 voltmeters used to measure voltage across each color diode. This voltage was used to calculate the current being generated by the diodes at varying light intensities. On the right side of the slide is the graph for each diode's response to blue light for 3 different distances. Important notes about this data include that as the light source is being moved away from the sensors, the voltage and therefore current decrease as you would expect. Also, the blue diode has a significantly higher current output compared to the red and green diodes. These factors were something I had to consider when developing the algorithm and the firmware code. The firmware has a very lengthy and complex procedure to run all its processes, so I created this general flowchart as an overview of how it operates. On initial power-up, we begin on the leftmost diagram indicated with the black startup state that puts the unit into an idle position. Here it detects we are running for the first time and sends it to the calibration state in the middle. Calibration reads the current light settings from voltage levels on the sensors and creates a threshold value using the averages over 5 seconds. Then we are returned to the idle state where a user input is needed to start the testing of LEDs. After a command to test, the state machine waits for an LED to be present to begin taking measurements depicted in the diagram on the right of the slide. Here we use a timer to determine the length of the LED's on time, an algorithm that determines its color, and then a second algorithm to determine what pattern of LED blinks is being shown. Here are pictures of 2 differing setups that I worked with throughout the project. On the left, we have development boards that I used while the PCB was being designed and assembled, along with part of the sensor testing setup. On the right is the testing setup I used after receiving the PCB and accompanying power supply. The development board here is used to simulate the light patterns that we tested on. In conclusion, our team was able to complete the development of a prototype device that detects the light being emitted by LEDs. We began the year by researching and testing our photodiode sensors to understand how they could be used to detect light and determine its different colors. While designing the PCB, we concurrently used our development board to test the beginning of our detection algorithm and firmware. When the completed PCB arrived, we were able to integrate our existing firmware and use LEDs to test how well our algorithm was performing. Finally, we had our mounting solution 3D printed to secure our prototype to VoltServer's TX550 and create the finalized documents to deliver to our technical directors, such as the user manual and bill of materials. We would like to take this time to thank VoltServer for sponsoring this project and our technical directors Camilo Giraldo and Stanley Milnek for overseeing our progress. We want to thank Mike Smith for his support in answering our questions and give a huge thank you to Dr. Sunak for running an amazing capstone program this year. Thank you.